Today I want to talk about what has been regarded as the hardest problem in classical physics. The problem of describing the motion of fluids. A problem that is fundamentally linked to our perception of the world. I want to talk about why it is so hard, and how we have to deal with it on a daily basis for all kinds of engineering applications. Okay, so the first thing that you need to know is that this problem doesn't have any fancy physics. There is no quantum mechanics or general relativity or things that are extremely fast or big or small or hot or cold. Absolutely none of that. This is just classical Newtonian mechanics. And the most difficult part of the problem can be described by using only two principles. Conservation of mass, meaning that mass is not created or destroyed, and conservation of momentum, that you may have heard before as force equals mass times acceleration. These are well-known principles, but when you put them together on a fluid, they could become very hard to solve. But then the question is, why? Well, in a nutshell, there are two main reasons. The first one is that the problem exists on a continuum, and the second one is that it is a highly nonlinear problem. Being on a continuum, it's a problem because it means that we have to solve an infinite number of degrees of freedom. Okay, so if you think about an easy problem on physics, like a pendulum or describing the position of a ball in 3 dimensions, those have 1 and 3 degrees of freedom respectively. You only need to know the angle or the XYZ position in order to solve the problem. But in fluid mechanics, to solve the problem means to find the velocity and the pressure everywhere. And if you have a continuum, that everywhere means that in every point, and there are infinite points, you will have to find a value for velocity and pressure. And of course, solving an infinite number of degrees of freedom is harder than just solving a few. The second reason, being a nonlinear problem, of course makes it more difficult than if it was just a linear one. Now, the reason why this is a nonlinear problem is because it's related to a transport equation. Transport equations can tell you how one variable, like for example temperature, is being transported by the velocity in some field. In that case, the velocity is an input and you just find the distribution of temperature, which is not that difficult to do. However, when you're describing the motion of fluids, the quantity that you're transporting is momentum. And momentum is mass times velocity, which is being transported by the velocity. So it's like the velocity is transporting itself. That's what's making this problem not linear. Now, it's important to mention that both of these ingredients must be present in order to make the problem very hard. If only one of them is present, like for example, if the problem is not linear but also not in a continuum, then you end up with something like a double pendulum or the Lorentz attractor. These problems are far from being trivial, but also not the hardest problems ever. And part of this is because they have a few degrees of freedom, like only 2 for the double pendulum and 3 for the Lorentz attractor. It would be much harder if they were a problem in a continuum. The other scenario is also possible, a problem that is described within a continuum, but the nonlinear part is not very strong. For fluids, that would be the case of laminar flow. Flow that is characterized by being very smooth and relatively easy to describe. And that would also be the case of solid mechanics, where the deformations are not very big and not very fast. It would be described by pretty much the same equations, but the nonlinear part is not very strong, because as you know, solids do not deform as much as fluids. Now, to be clear, I'm not saying that these problems are easy. They are not. But because the nonlinear part is not the main driver of the dynamics, they do not have turbulence. Which takes me to the next point. A detail that I haven't mentioned is that not every nonlinear interaction is the same. Some are much harder than others. The quote-unquote easy nonlinearities have terms that are like x squared or velocity squared or x times y, which would be the cases for the double pendulum and the Lorentz attractor. For fluid mechanics, the nonlinearity, however, is the velocity times its gradient. If this term is large enough, it will tend to move energy from very large swirls, like large structures in the flow, to smaller and smaller ones, creating a fractal nature. These would, so to speak, open the gates of hell and unleash what we refer to as turbulence. An extremely hard physical problem, but that is also pretty awesome. Richard Feynman was one of those referring to turbulence as the most important unsolved problem in classical physics. And on his deathbed, it is reported that Heisenberg put it like this: "When I meet God, I'm going to ask him 2 questions. Why relativity and why turbulence? I really believe he will have an answer for the first." which might give you an idea of how challenging this is. On the other hand, turbulence is all around us. It has been described by scientists, engineers, and artists. It is deeply rooted in our language and our way of describing the world. It is usually linked to words like chaos, disorder, roiling, and changing, which is not a coincidence. And yet, mathematically, it has challenged some of our brightest minds for more than a century, and we haven't been able to solve it. So, what is turbulence exactly? You probably have a good intuitive idea of what it is, but there is not an agreed formal definition of turbulence. However, we know that it has certain characteristics. Like, it is unpredictable, meaning that although it is deterministic, it is chaotic, which makes intuitive sense given how messy it looks. We also know that it covers a wide range of scales. The largest swirls or eddies in a flow are in the order of meters for engineering applications, and like kilometers for meteorology, and millions of kilometers for stars or gas clouds in astronomy. These big eddies transfer their energy to smaller and smaller eddies up to the smallest size, which could be in the order of micrometers, where all the energy is finally dissipated into heat. This means that it is also dissipative, as kinetic energy is transferred to smaller scales until it is transformed into thermal energy. It means that it is also diffusive. As it transports energy from a wide range of scales, it spreads everything everywhere, which is really good for mixing applications. Now, because it's chaotic, it means that it is also unsteady, which means that it changes in time. And it also has to be at least 3 dimensionals, which allows the flow to find a path to swirl around itself to twist chaotically. So from this list you can see that there are several mechanisms within turbulence. And by themselves, they don't seem super complicated, but when you put all of them together at the same time, it can get very complex. So in a sense, turbulence is similar to poker or chess, meaning that the rules of the game are relatively simple, but it gets very difficult very fast. And all the shenanigans that I've said so far can be described with only 2 equations. They represent the conservation of mass and momentum in a fluid volume, and they are called the Navier-Stokes equations. In the year 2000, the Clay Mathematics Institute offered $1 million each for the solution of 7 key problems in math, the Millennium Prize problems. These are profound and extremely difficult problems in math, for which even understanding the question could be really hard. And Navier-Stokes is one of them, by far the problem that is the most related to physics and our daily lives and engineering. Out of the 7 problems, only 1 has been solved and is not Navier-Stokes. The formulation of the Millennium Problem asks for the proof or disproof of the existence and smoothness of solutions to Navier-Stokes, meaning that you don't even have to find the solutions, you just have to prove that they exist, or that they don't. With that said, we are not completely clueless about the solution. For example, think about the mixing of 2 fluids, like coffee and milk. At the beginning, the system is very easy to describe, you just have milk on one side and coffee on the other. However, as you start mixing, the system becomes more complex and chaotic, it becomes turbulent. And then, after some time, the mix is complete. Everything looks brown everywhere and the velocity is slowly dissipated. This is also easy to describe. It is just brown everywhere and slowly moving. In that case, the complexity of the system is only really high in the middle, when mixing is happening. We do know that the solution exists very shortly after the system begins, and after a very long time, when dissipation has taken place. But in the middle, when things are messy and complexity is high, that's where we don't know if a general solution exists and if it's smooth. Okay, now we have described this Millennium Problem, which of course is super challenging. But that's not even the worst case scenario. If you mix what we have described so far with other physics, you will get a lot of kinds of shenanigans. For example, if you get the flow really fast, like close to the speed of sound fast, it is going to compress. And when you compress a gas, it heats up. So now you need temperature and you will get shock waves and boom, supersonic, hypersonic flow, which is a completely different beast. Or if, for example, now you make the flow respond differently depending on how fast you apply the forces, then you get a viscoelastic behavior, which is also pretty weird. Or if it's electrically charged, then it's going to answer to external electromagnetic fields, creating what's called electrohydrodynamics. and then you'll be able to model things like plasma inside of a tokamak for fusion energy production, or the inside of a star. Okay. But if it's so difficult, then how do we deal with it all the time? I mean, airplanes fly, there is water coming out of the sink anytime you want, and all sorts of applications from pharmaceutical to heat transfer, ventilation, naval, aerodynamics, aerospace, all of them require to model fluids, and they work. How do we do it? Well, in general, the flow could be very difficult, but that is not always the case. If things are very small, or very viscous, or very slow, like moving honey, or the movement of a bacteria, or an insect moving through water or air, or applications in lubrication, for example, the flow is not turbulent, it's laminar. And that can be more easily solved. Now, when we have turbulence, we can do approximations to solve the flow where the turbulence is not super important. Or we can do approximations to the equations in order to find averages of the flow or average fluctuations. It will be very computationally demanding, and it will not solve every little detail in the flow. Not every length scale is going to be part of the solution, and it will not capture every fluctuation. But it is good enough for most applications. However, when it comes to turbulence modeling, some researchers say that our models of turbulence are good enough for problems where turbulence doesn't matter. Meaning that despite not doing a terrible job, they are far from perfect, and there's still a long way to go. But on the other hand, if we can do okay with what we already have, then who cares about an analytical solution? Well, that's the thing. We are doing just fine, but we can do much better. And potentially the world would become a radically different place if we had an analytical solution to Navier-Stokes. For instance, for what we are doing today, every engineering design related to a fluid would become optimal. Not just very good, but optimal. It would be more efficient, it would consume less energy or produce more energy, and the overall manufacturing process could be even cheaper. It would be a significant boost to every industry somewhat related to fluid mechanics, and there are a lot of them. For example, we would be able to extract way more energy from almost every source, and then because we're using it more efficiently, we would consume less energy, thus helping the energy crisis. We would be able to predict the weather with unprecedented accuracy, which would help stuff like food production. And it would also help manufacturing, not just by making things cheaper, but also potentially helping us to unlock new materials in an industrial scale, such as superconductors or carbon nanotubes. It almost feels like a solution to these equations would kickstart a chain reaction of technological development, similar to how the Industrial Revolution was enabled by tools like calculus. And in that sense, a profound understanding of fluid motion would help us to finally become a Type 1 civilization, and perhaps helping us unlocking new things like commercially viable fusion energy, the ability to terraform planets, or to travel to other stars. It's kind of similar to how in civilization games you have to uncover some technologies first before you can move on to others. After all of that, you look back and it seems like what we're looking for is a simple description of a very complex problem, which it's a bit paradoxical. But as Chopin put it, simplicity is the final achievement. And complex systems are one of the greatest challenges that we are facing right now. And it's not just turbulence. For example, in chemistry, we understand the basics, but scale it up and then protein folding becomes very difficult very fast. Or in biology, we understand how a few neurons interact and communicate, but put enough of them together and they become a brain. And we are unable to understand its properties like, consciousness. Then in comparison, it almost seems like turbulence is one of the easiest unsolved problems that we're facing. Or not, we don't know. But in any case, it cannot be denied that there is something beautiful, familiar, and very hypnotizing within turbulent structures. And as Dostoevsky put it, beauty will save the world.